Welcome back, everybody, for another deep dive. This time we're going exploring the world of electrostatic potential and capacitance.
Yeah, we're going to be cracking open a physics textbook today.
And it's amazing how this stuff, it's everywhere.
Yeah.
Did you know, the tiny flash in a camera
Yeah.
actually uses a capacitor to discharge like a burst of energy.
Yeah.
It's like a microscopic lightning bolt,
It is.
all thanks to electric fields.
And it's really interesting because, even though it's everywhere,
Right.
the actual physics behind it is kind of hidden, you know?
Yeah, totally.
So we're going to, peel back those layers today.
Yeah, for sure. Okay, so let's unpack this a little bit.
Okay.
The book starts by laying the groundwork with this concept of conservative forces.
Right.
What exactly makes a force conservative anyway?
Well, it's all about where the work goes. So think of, lifting a book up.
Okay.
Gravity's pulling it down. You're putting in effort to raise it. And that effort you're putting in becomes potential energy, which is stored in the book.
Okay.
Due to its position. And a conservative force means no matter how you lift that book, whether you lift it straight up or you take it on some weird zigzag path or you even use a pulley system to get it up there,
Yeah.
the work done and thus the potential energy only depends on where you started and where you ended.
So with a non-conservative force, then friction or something,
Right.
some of that effort's wasted as heat.
Exactly.
But here, with conservative forces, it's neatly stored.
Yeah, it's all accounted for.
Okay, and this ties into electrostatics, how?
Because just like gravity, the Coulomb force, that's the force between charges,
Right.
is also conservative.
Right.
And that's huge because it means we can assign a potential energy value to a charge
Okay.
at any point in the field, regardless of how it got there.
Okay.
And that really lays the foundation for understanding this whole idea of electrostatic potential.
Okay, so if I'm picturing this right in my head, it's like each charge creates sort of like an energy landscape around it.
Yes.
The potential is a measure of how much uphill effort it takes to move another charge to a specific spot on that landscape.
That is a really insightful way to think about it. And just like a ball rolling downhill, a positive charge will move from a region of higher potential to lower potential.
Okay, that clicks.
Good.
So potential difference, that's like the steepness of our landscape.
Exactly.
And the textbook talks about calculating this for different charge setups. If you have just 1 point charge sitting there.
Right.
Seems pretty straightforward.
Yeah, distance is key there.
Okay.
The further you are from that charge, the weaker its influence, and thus the lower the potential.
Okay.
And it's an inverse relationship, so it falls off as 1 over r, where r is that distance.
Makes sense. Yeah, the influence fades with distance.
Right.
But then it gets more complex with things like electric dipoles.
Right.
It's not just distance anymore, right?
Right. Now we've got to bring angle into play.
Okay.
So a dipole, remember, it's like this tiny plus and minus
Right, yeah.
pair of charges. So depending on where you are relative to that dipole, you might be closer to the plus end, you might be closer to the minus end.
Right.
And that's going to affect the potential. So that's where the angle between your position and the dipole's orientation comes in. And the potential falls off faster there. It falls off as 1 over r squared,
Okay.
meaning its influence diminishes more quickly compared to a single charge.
So the landscape is more directional.
Exactly.
It matters not just how far away you are, but from which direction you're approaching that dipole.
You got it. And imagine now a whole bunch of charges. Each one of those is creating its own mini landscape.
Right.
What's amazing is the overall potential is just the sum of all those individual contributions.
Whoa.
And that's what we call the superposition principle.
So it's like each charge is dropping a pebble in a pond, and then all the resulting ripples just add up to make the final wave pattern.
A great way to think about it, yeah.
Okay, I'm starting to see how this potential idea helps us analyze these complex situations.
Absolutely. Now, to visualize these potential landscapes, the textbook introduces this concept of equipotential surfaces.
Okay.
And you can think of these like contour lines on a topographic map.
Right, so all points on the same contour line are at the same elevation,
Yes.
and all points on the same equipotential surface have the same electric potential.
Exactly.
I'm digging this visual analogy.
Good.
But how does that tie back to the steepness that we were talking about earlier?
So here's where it gets really cool. The electric field lines, which show the direction of force on a positive charge, are always perpendicular to these equipotential surfaces.
Okay.
So the closer those contour lines are together, the steeper the potential gradient and the stronger the electric field in that region.
So if those contour lines were like really bunched up,
Yeah.
that's where a charge would feel the strongest push or pull.
Exactly.
It's kind of like a ball rolling down a really steep hill.
That's a fantastic way to picture it. And the textbook actually has a figure
Oh, cool.
showing these equipotential surfaces for a couple different charge arrangements,
Okay.
like a dipole or two positive charges. And it really helps to visualize how those landscapes take shape.
Okay, I'm definitely going to check that figure out later. This is starting to feel less abstract and more like something I can actually picture.
Good.
Okay, so how about we take all of this,
Okay.
and now we can start thinking about how systems of charges behave, because that's like the next step, right?
Yeah, absolutely.
Really?
We can delve into how the potential energy of the whole system comes about and why it matters.
Right. Let's tackle that energy puzzle.
Sounds good.
All right, so we've talked about these potential landscapes created by charges.
Right?
Now let's dive into how we can actually calculate the potential energy of a whole system of charges. It seems like this would be a lot more complicated than just dealing with like a single charge.
It definitely gets more intricate.
Yeah.
But the core idea is the same.
Okay.
It's all about the work done
Yeah.
in assembling that system.
Okay.
So think of it like this.
Okay.
Imagine you have a bunch of charges just scattered far apart.
Mm-hmm.
And to bring them together into some specific arrangement,
Right.
you have to work against those electrostatic forces,
Okay.
either pushing like charges closer together or pulling opposite charges together.
So the potential energy of that final configuration
Yes,
represents the total effort it took to arrange those charges.
exactly.
Like almost like building a tower of blocks or something.
Yeah.
Each block representing a charge. And the higher you build that tower,
Yeah,
the more potential energy the system has.
that's a fantastic analogy.
Okay, cool.
And the textbook actually walks through an example with charges arranged at the corners of a square,
Okay.
calculating the total potential energy of the system. And it's a nice step-by-step process that really highlights how the final arrangement determines the potential energy.
So it's not just about individual charges and their potentials. It's about
Right.
the interactions between all of them within the system.
Exactly.
Okay, I'm starting to appreciate the interconnectedness of all this.
It's all connected.
And this interconnectedness becomes even more apparent, I think, when we start introducing conductors into
Yes.
the mix.
Yes.
Conductors, unlike insulators, have these free charges
Right.
that can move around,
Exactly.
right? It's like those free charges have a backstage pass to the whole conductor.
Yes.
But how does that affect the electric field inside?
So it's pretty remarkable, actually.
Okay.
Those free charges, they're going to redistribute themselves
Okay.
until they completely cancel out any electric field
Whoa.
within the conductor.
So no matter how strong the external electric field is,
Yeah.
the inside of the conductor remains this field-free zone.
It does.
That seems counterintuitive.
Yeah. It is. It's a consequence of those mobile charges always seeking equilibrium.
Okay.
And that has some fascinating implications.
Okay.
For example, any excess charge on a conductor will always reside on its surface.
It's like the charge is being pushed to the edge like people on a crowded subway car.
Yeah, that's a good way to think about it.
Okay. But why does that happen?
Well, because if any of that excess charge were inside the conductor,
Right.
it would create an electric field.
Right.
And we know those free charges are immediately going to move
Yeah.
to neutralize that field.
Right.
So the only stable configuration is for all that excess charge to hang out on the surface.
So it's like the surface of the conductor is acting as a shield,
It's
protecting the inside from any electric field shenanigans.
Exactly.
And this shielding effect has some practical applications too, right?
Absolutely.
Like Faraday cages,
Yes.
those conductive enclosures
Right.
that can block out external electric fields. You might have seen them used to protect sensitive electronic equipment, or even in some museums to demonstrate the principles of electrostatics.
That's right.
Like a force field
It is.
against electric fields.
Against electric fields.
And it all comes down to those mobile charges within the conductor.
That's right.
Okay, now speaking of influencing electric fields,
Yes.
let's switch gears and talk about dielectrics.
Oh.
These are materials that don't conduct electricity very well, right?
Right.
Think like rubber or glass.
Yeah, good examples.
So they're like the opposite of conductors.
Yes.
But what happens when you put a dielectric in an electric field?
Good question.
Does it just sit there and do nothing?
Not at all. No, dielectrics have a very interesting response to electric fields.
Okay.
Remember how atoms have positive charges in the nucleus
Right.
and negative charges in those electrons?
Yeah, basic atomic structure.
Right. Protons and neutrons hanging out in the nucleus, electrons buzzing around in their orbitals.
Yeah.
Well, when you apply an external electric field to a dielectric,
Okay.
those charges within the atoms or molecules, they shift slightly.
Okay.
It's like the electric field is tugging on the positive and negative charges in opposite directions.
So the atom or molecule gets stretched out a bit, like a tiny rubber band.
A great analogy.
Okay.
And this creates what we call an induced dipole moment within each atom or molecule.
Okay.
They become like tiny little dipoles themselves.
So each molecule is like a tiny plus and minus pair.
Yes.
And the electric field is trying to line them all up.
Exactly.
Yeah.
And this alignment of dipoles within the dielectric, it creates its own electric field.
Oh, wow.
But this field opposes the external field.
So it's like a battle of the electric fields.
It is. It's like the dielectric is pushing back
Okay.
against the electric field, trying to permeate it.
But the dielectric can't completely block the external field, right?
Right.
It's not a perfect conductor.
It's more like a partial resistance.
Okay.
The dielectric reduces the strength of that electric field.
Right.
Mm-hmm.
But it doesn't eliminate it completely.
And the extent to which it can do this is characterized by something called the dielectric constant, right?
Yes, exactly.
So a higher dielectric constant means a stronger ability to weaken the electric field.
Precisely.
Okay.
And this property of dielectrics is crucial for understanding how capacitors work.
Capacitors.
Yes.
Those charge-storing devices that are everywhere in electronics.
That's right.
I remember them being a bit of a mystery back in my physics classes.
Yeah.
So a capacitor, just to remind myself, it's essentially just two conductors separated by an insulator.
Often a dielectric material, yes.
So it's like a sandwich.
Yeah.
With conductors as the bread and a dielectric as the filling.
Perfect analogy.
Okay. But how do they actually store charge?
It all comes down to potential difference.
Okay.
When you apply a voltage across that capacitor, charges build up on the plates.
Okay.
Positive charges on one plate, negative charges on the other.
And the amount of charge that that capacitor can hold at a given voltage is called its capacitance.
So a capacitor with a high capacitance is like a large container for charge.
Exactly.
It can hold more electric juice at the same voltage.
That's a great way to think about it.
And you know what's really interesting is that the capacitance of a capacitor depends on both its geometry.
Yes.
So the shape and size of those plates and the distance between them and the type of dielectric material used.
That's right.
So the filling in our sandwich analogy is actually pretty important.
It is.
But why does the dielectric matter so much?
That's a great question, and it leads us into even deeper waters of this capacitor world.
Right.
We'll explore how dielectrics actually enhance the ability of a capacitor to store charge.
Okay.
It's a key insight into how these tiny components play such a huge role in modern technology.
All right, let's unpack this dielectric mystery.
Right.
All right, so last we left off, you were about to reveal the secret of how dielectrics boost a capacitor's ability to store charge.
Right, yeah. It's like they have this hidden superpower.
Yeah.
And they do in a way.
Good.
So remember, a dielectric reduces that electric field strength between the capacitor plates.
Right.
And it does this because of those aligned dipoles.
Yeah.
Creating an opposing field.
Right. It's like they're partially resisting that
Exactly.
electric field trying to permeate the space between those plates.
Yes, and that resistance is key.
Okay.
Because the potential difference between those plates is directly proportional to the electric field strength.
Okay.
A lower field strength means a lower potential difference.
Okay.
But here's the crucial part. The charge on the plates remains the same.
Hold on, let me wrap my head around this.
Okay.
Same charge,
Yeah.
but lower potential difference.
Yes.
And since capacitance is the ratio of charge to potential difference,
Right.
that means the capacitance increases.
That's exactly it.
Okay.
It's like the dielectric is making that capacitor more efficient
Wow.
at storing charge. And the amount of that increase is directly proportional to the dielectric constant of the material.
So a material with a higher dielectric constant is like a turbocharger for a capacitor.
Yes.
It could really ramp up its storage capacity.
A great analogy.
Okay.
Now, to really understand how these capacitors behave in circuits,
Right.
we need to talk about how we can combine them.
Right.
Just like we combine resistors.
Right. I remember series and parallel combinations from my physics days, but it always felt a bit like a puzzle.
Yeah.
Figuring out how the overall capacitance changed.
It's definitely a bit of a mental workout.
Yeah.
So let's start with capacitors in series.
Okay.
Imagine two capacitors connected end to end,
Okay.
like carriages in a train.
So the positive plate of one is connected to the negative plate of the other.
Precisely.
Yeah.
And the key here is that the charge on each capacitor in a series combination will
Well,
be the same.
That's interesting. Why is that? It seems like one capacitor could potentially store more charge than the other.
So think about what would happen
Okay.
if one capacitor tried to hoard more charge
Right.
than its neighbor in that series chain.
Right.
That imbalance would create a potential difference
Right.
between the connected plates.
Okay.
And charges would immediately flow until that potential difference is zero.
Gotcha.
It's all about maintaining that equilibrium.
So the charges have to play fair
Yeah.
and distribute themselves evenly
Yeah.
across that series combination
Exactly.
to keep everything balanced.
Right.
Okay, that makes sense.
And because those charges are the same
Mm-hmm.
across all the capacitors in series,
Right.
we can derive a nice little formula for the total capacitance.
Okay.
1 over C
Okay.
equals 1 over C, 1
Mhm.
plus 1 over C, 2, and so on for however many capacitors you have.
So the reciprocal of the total capacitance
Yep.
is the sum of the reciprocals of the individual capacitances.
You got it.
It's like the opposite of how we add resistors in series.
It is, yeah.
Okay.
All right, so now let's switch tracks.
Okay. To capacitors in parallel.
Okay.
Here, we imagine our capacitors connected side by side,
Okay.
like books on a shelf,
Mm-hmm.
with their positive plates all connected together
Right.
and their negative plates all connected together.
So they're essentially sharing the same potential difference.
That's right.
Okay.
And in this setup, the total charge stored is simply the sum of the charges
Okay.
on each individual capacitor.
That makes sense. It's like having two containers side by side,
Yeah.
each holding water.
Right.
The total amount of water is just the sum of the water in each container.
Perfect analogy.
Okay.
And this leads to a nice straightforward formula for the total capacitance in parallel.
Okay.
C equals C1 plus C2 and so on for however many capacitors you have.
So adding capacitors in parallel
Yeah.
is just like adding resistors in series.
That's right.
You simply add up their individual capacitances.
Okay.
Okay, that's much easier to remember than the series formula.
It is.
And the textbook even walks us through this like example problem. Yeah.
With a network of capacitors
Right.
connected in both series and parallel,
Yes.
showing how to break down the problem step by step
Right.
to find the total capacitance and the charge on each capacitor.
It's like solving an electric circuit puzzle.
Yeah, exactly. It's like, where do you even start?
Yeah.
Okay, now speaking of puzzles, one thing that always baffled me about capacitors is this idea that they store energy.
Okay.
Where is that energy actually stored?
That's a great question.
It's not like charges are little batteries
Right.
packed inside.
No, it's not like little tiny batteries in there.
Okay.
The energy is actually stored within the electric field between those plates.
Okay.
Remember, it takes work to charge up that capacitor
Right.
to move those charges
Yeah.
against those electric forces.
So it's like stretching a rubber band.
Yes.
You put in energy to stretch it.
Yep.
And that energy is stored as potential energy waiting to be released.
Right.
And in a capacitor, that stretching is the work done to build up the electric field.
You got it.
Okay.
And the textbook gives you a couple different formulas for calculating that energy stored in a capacitor using either the capacitance or the charge or the potential difference.
And I remember there was also this concept of energy density, right?
Yes.
Something about how much energy is packed into each tiny bit of space
Exactly.
within that electric field.
That's right. The energy density is proportional
Okay.
to the square of the electric field strength. So if you double the field strength, you actually quadruple
Wow.
the energy density.
Okay.
That's why these capacitors can be such powerful energy storage devices,
Right.
especially when you consider how strong those electric fields can be.
Wow, that's impressive.
It is.
It's like capacitors are these tiny little powerhouses
Yeah.
storing energy in these invisible fields between their plates.
It is remarkable.
And then the textbook ends with this example
Yes.
involving two capacitors,
Right.
one charged and one uncharged.
Yeah.
And when you connect them together, some of the energy seems to disappear.
It does. It's a very interesting scenario.
Wait a minute, energy can't just vanish.
It can't just vanish, no.
What's going on there?
So it doesn't vanish completely.
Okay.
But here's something to ponder.
Okay.
During that split second, when charge is flowing
Right.
between those capacitors,
Yeah.
some energy is inevitably lost as heat
Okay.
and electromagnetic radiation.
So it's a reminder that real-world systems
Yes,
always have some inefficiencies.
they do.
It's like trying to roll a ball down a hill.
Yeah,
Some of that energy will always be lost due to friction with the ground.
Exactly. It's a fundamental principle of physics
Right.
that energy can't be created or destroyed,
Right.
only transformed from
Wow.
one form to another.
So while that energy stored in the capacitor's electric field
Right.
might seem to vanish,
Yeah,
it's really just being converted into
exactly.
other forms.
That's right.
This has been an incredible deep dive
Yeah, it has.
into the world of electrostatics,
It's fascinating stuff.
potential and capacitance.
It is.
We've covered so much ground, from the fundamental concepts of conservative forces to the intricate workings of capacitors and the surprising role of dielectrics.
It's amazing how much is packed into these seemingly simple devices.
Yeah, totally. I feel like I've gained a whole new level of understanding
God.
of this invisible world of electric forces.
It's a hidden world, but it's all around us.
Yeah, it really is. And remember, everyone,
Yes,
this is just the tip of the iceberg.
it is.
We've focused on parallel plate capacitors,
Right.
but the world of capacitors is vast.
It is. There's so much more to explore.
Think about all the different shapes and configurations they can have,
Right.
and how those capacitances would be calculated.
Absolutely.
So until next time, keep those minds charged up
Yes.
and those questions flowing.
Keep that curiosity alive.